for the day is can we deal with things that are not functions per se? You might call them implicitly defined curves. I have a request to go back to the previous slide. So did you have a question there? Or you just needed to get something? Done. Okay. All right. So it would be hurtful to be like, we don't care about you, circles, right? Or we don't care about you, ellipses. Like maybe someone would like to calculate the slope on those things too. Wouldn't you like to? In fact, in a way, you just did. If you could express it parametrically, then you actually have a way to maybe. But we'll go in this direction. I think you'll like where we're going to go with this today. All right. So let's just let's apply some wishful thinking here. I want you to think, and I think we already have thought a little bit about this. Why it might be appropriate to take a derivative on both sides of an equation. Are you convinced that if I have one expression and you have another expression that's equal to my expression, and we take derivatives, that we should get the same thing? Think graphically about it, justify however you like, but it should certainly be true. The converse is not necessarily the case. We've seen that it's not true that you could have two different functions that have the same derivative, but it's certainly true that if you have the same thing as I have, and we both take derivatives, we should get the same thing, right? So I think it's okay. I'm just trying to build a little bit of at least an informal case that it is okay to take derivatives on both sides of an equation. If we haven't thought that's okay before, let's say it now. I mean, that could be a big new idea, couldn't it? To you, you can square both sides of an equation. All these different things you can do. You can take a derivative on both sides of an equation. So I'm about to take derivatives of all these things. Now, if we're thinking about eventually wanting to know the slope, I'd like to still think about y as if it's like a function of x. So that is, y is some unknown function of x. It's like y of x. Think of it as if it's a function. So we actually need to take these derivatives. I think some of these will be easy. Yeah. Okay. Okay. Yeah, I'm taking the derivative of both sides. Maybe I should have written that first. D dx of this and d dx of this. But I immediately applied the linear property. Yeah. Good. So the derivative of x squared is, of course, 2x. The derivative of 1 is, of course, 0. So far, so good. But I need to have a heart-to-heart with you about y squared. I need my clicker here, but these things highlight. So if y is a function of x, if it really is a function of x, who knows, y is, in more complicated situations, keep in mind that we're taking the derivative not with respect to x. I think that's the key here, right? The derivative of x squared with respect to x is 2x. But the derivative of y squared with respect to y is 2y, true. But that's not what we're taking the derivative with respect to. We're taking the derivative with respect to x. So how do we deal with that? Well, we've just been talking about that quite a bit, actually, about taking the derivative of y with respect to x where that's not. So what do we get? Well, we get 2y, but we still need to multiply by the derivative of y, don't we? Y is like a function of x. So this and this are not a huge jump for you. But this middle piece, I want to make sure you're convinced that that is in fact what we get, isn't it? By the chain rule. Let's let that sink in. Everything else on here you'll have no problem with. This is the thing you're going to have to think very hard about. Here, can you put that away? You can put it in your backpack and zip it closed so that it's not tempted. Again, if you have some function, right? Let's go back to yesterday for a second. If I have sine of x squared, we've talked about this. If you d dx that thing, you get 2 sine x away times cosine x, right? So I'm just saying this is the same situation. We have this complicated. I just want you to understand that that's not That's just not like an innocent y. That's a y that's like a function of x. So its derivative is also 2y times whatever that derivative of y is, right? It's still, I just note the parallelism here. It's the same situation, okay? It's exactly the same situation, and you can't ever forget a chain rule. You're just not allowed. Okay. All right, and then now what are we trying to do? Well, maybe we're trying to find the slope dy dx. So I think we're there, aren't we? Like all we need to do is isolate dy dx, and we'll have a slope formula here. Now, one thing that's interesting, of course, about the slope formula is that it involves both x's and y's, right? But is that okay? Sure. Yeah, it's not a problem. So the derivative dy dx is equal to negative x over y, which I think I feel bad here. I wrote up in the area where I'm going to put this, but here I'll erase it. If you're done with the writing I put up there, then I'll erase it. There's a point, and do you agree that that's on this circle? The original circle is a unit radius, right? So it has the point on it, for example, 1/2 comma root 3 over 2. Yeah. So what's the slope at that point? Notice you need both the x and y coordinate. What is that? It's 1/2 divided by root 3 over 2, make it negative, which comes out to what? Yeah, negative 1 over root 3, which actually doesn't really look like that, but whatever. I'm working on the PowerPoint here. But the point is, we can definitely still find slopes using this formula. First, we might need to find the point x comma y. We might need information not just about x. But this still does the job of finding slopes anywhere on this circle. What's the slope at when x is 0? Regardless of what you get for y from this equation. If x is 0, you'll get a slope of 0, which confirms. And again, if the slope, what if y is 0? That is, what if we're either here or here? We get an undefined slope, which also makes sense to us. And then everything in between makes sense to us too. What if we're at the point root 2 comma root 2? We get a slope of negative 1. Right? So this seems to be doing what we want it to do. So this actually provides, we did some parametric stuff with a circle in the warm-up and found some slopes using that technique. But now we have an interesting new technique using implicit differentiation, which works of course not just for circles, but for other more exotic examples too. Oh, I guess I'm illustrating that, of course, because x and y, anytime you're in opposite quadrants, you'll get the same slope, won't you? Right? Right, okay. So we can do more exotic things, right? Here's one, for example, that cannot be solved for y. On the last one, you might be like, well, that was neat, but I really don't like this, and I prefer to just solve that for y. Well, here you don't have that option, right? And also, I don't know what this looks like. I don't have any intuition really about this at all. And yet I can still ask the question, what is dy dx here? Marcus has a question. Sorry.
Where did dy over dx come from?
Where did the dy dx come from? Down here, you mean?
Yeah, right there.
Yeah, so I erased it right here. But I was convincing, here, I'll write it again. I was trying to convince you that the chain rule applies. And that when we take the derivative of y squared, for example, it works the same way. Do you agree with the top line up there?
Yeah, I did.
All right, well then I say you must agree that this also holds. Do you agree?
Yes.
Yeah? All right, that's all we did. Didn't you just say the derivative of y squared with respect to x is 2y dy dx? That's what you said. So we're going to start by doing the same thing. Go ahead and see if you can predict the next line if you like. We're going to take derivatives on both sides. Anything that has only an x is going to be not a problem for us. What's the derivative of sine y? Maybe I should have Marcus say. What's the derivative of sine y with respect to x? Close. Times y prime, yeah. Okay. What's the derivative of 2y with respect to x? Yeah, it's simply 2 times dy dx. You might be thinking, what, don't you have the chain rule to do there? Well, sure. What's the derivative of y with respect to x? Excuse me, y with respect to y. There's just 1, okay, and then multiply by dy dx. That would be one way to think about it. But it's certainly true that the derivative of 2y with respect to x is equal to 2 times the derivative of x with respect to y. Excuse me, of y with respect to x. We can factor out the 2, that's one of like the linear properties, right? And that is just another name for dy dx, isn't it? I mean, that's another way of writing dy dx. One way or another, realize that, I mean, the chain rule kind of is there on the first term, but it's also kind of not necessary. You don't really have a function of a function. This is where the chain rule really shines on the last term there. All right, so there was the chain rule in action, and there's us taking the derivative of both sides. And then remember, our goal here is to find dy dx. So the rest of this is algebra, right? Well, the algebra was fairly trivial on the last slide. Well, on this one, we need to do a little bit of work. Yeah. Move everything that has a dy dx over to one side, move everything that doesn't have a dy dx over to the other side, and then what? Huh? Yeah. Factorize that equation, and then divide by 2 minus cosine y. I hope your algebra skills are strong coming into this, and that you're okay with all those steps. The calculus ended right here, right? So there we have it. We have the derivative. Again, it has an x and a y in it, and that's just fine. That's not a problem for us, right? And if we haven't said it already, this is the technique we're calling implicit differentiation. Easy 2-step process. Differentiate both sides with respect to x, that's the key, and that's why the chain rule arises when we're dealing with y. We're not taking derivative with respect to y. We're taking it with respect to x. And then do algebra. Here's some algebra. Albert.
Okay, so dy over dx, that's like our final destination.
Correct. I mean, yeah, there were no x. There should have been instructions on this example. Find dy dx or something. Find the derivative or something. So let's give this guy a try here. We've got x squared minus xy plus y squared equals 7. Sorry, that wrapped lines here. At negative 1, 2. Is that on the curve? Yeah, hopefully. 1 plus 2 plus 4. Yeah, it is on the curve, equals 7. All right, the negative 1, 2 is a point on the curve, apparently. So notice here's a context which doesn't necessarily immediately ask for implicit differentiation, but it should be very clear that that's the way to go. It is actually maybe possible to solve for y there, but not desirable. I would rather not. That would be like its own conversation. How do you even solve that for y? I think you could do it though. Yeah, you complete the square, quadratic formula or something with an x in it. So go ahead and try this. Let's take the derivative of both sides of that original equation. We need dy dx, don't we? Be careful of the 2 y's. I understand what the derivative of x squared is. I understand what the derivative of 7 is. And now I also, because we've already talked about it, I understand what the derivative of y squared is now, too. It's 2y y prime. What's going on with the xy? Say like the unit progression. Huh? Product rule, yeah. Right? Isn't x times y? It's exactly like as if you're taking the derivative of like x times sine x or something, right? Keep in mind that y is a function of x at all times, right? Do you agree that that's the correct use of the product rule in the brackets? Again, that should be the only surprise there, is this little piece that's new on this example. How the product rule feels in this new environment. comfortable with that? I mean, then the rest again is just going to be algebra, solve for dy dx. That's like the big move right there. And the calculus is basically done now, right? Now it's just algebra. So make sure to stop me if you have an issue there. Be careful with your sign, you know, distribute the negative, move everything that has a dy dx over to one side and everything that doesn't to the other, solve for dy dx. Like I said, the rest I'm just going to I want to skate over the details there. It's just algebra. Are you good on this step here? Go ahead. Yeah, so again, let's think about this as if it was like x sine x. How would you take the derivative of that? You go ahead. This is a prime. Here, go ahead and take the derivative. Good, right? So in general, what if it was xy prime? Wouldn't that be x times y prime plus y? I believe you just said, I think you just answered your question, right? Where does the y come from? It comes from doing the product rule. Isn't it the derivative of x times y? Yeah? All right. If we want the slope at -1, 2, go ahead and plug that in, x and y appropriately. It asks for the slope of the tangent line, or the equations of the tangent and normal to the curve. So let's start by finding the slope dy dx, and then we'll go out all the way and answer the question. I think the interesting part of this question is somewhat done, but so you should get 4/5. So if the slope is 4/5, then the tangent line, we have the point and the slope, so like I said, I don't know if I need to even show you this. You can just write down the equation of the tangent line and the equation of if someone asks you to do this, I don't think anyone ever will though. I can't think of anyone who has ever asked me to do that. Okay, so we'll just go with this. The first box is almost always sufficient. And the normal, we could easily write those things down. Yeah, so I don't think that anyone will ever ask you, but if you really like y equals mx plus b, then you can get it if you really love that form. Kind of rather not though. It's actually much less useful to me in this form than this one. I kind of like that. It's prettier. Okay. Is that cool? I want to say one more thing about the second derivative. See if we can get that in the last 2 minutes. Because you might think, oh, we maybe just do the process again, which is correct. But things do get a little tricky here. In fact, you know it because there's a dagger on the slide, right? Okay. So let's do the first derivative. Again, the first derivative, this shouldn't be too bad. We've already dealt with y squared. Yeah?
Please pardon the interruption for a few afternoon announcements. First of all, boys basketball workouts will be on or after school for those of you that have gotten your physical.
So far, so good.
Please meet Coach Turner by the weight room. Workouts will be from 2:45 to 4 p.m. We also have 2 homecoming reminders. Thursday is theme day. Freshmen is Western, sophomores sci-fi, juniors fairy tales, and seniors superheroes. There should be no masks or props resembling weapons brought to school. And the second reminder, you may not resell your homecoming ticket because the name on our list must match both your ID and the ticket number. Again, you may not resell your homecoming ticket. Thank you and have a great afternoon.
All right, so the last piece there. So now I think you're good on this. I don't need to talk about this at all. That's just what we've been doing all today. How do we take the second derivative of this? Keep in mind that these are both functions here. This is a function of x. This is also a function of x. How do we do the derivative of f over g? Well, we need the quotient rule. Hopefully you see its correct application there, right? You got bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. But then, let's not stop there, even though technically that's correct. Y prime is a thing we know in terms of x and y if we want it. So make the substitution, please. If you can give me the derivative, the second derivative, excuse me, in terms of just x's and y's, then do it, right? Albert has a
So
question.
is it right that in our work, will this substitute dy with the y prime instead of
Yeah, absolutely. Yeah. dy dx, y prime, either one is fine. We're trying to emphasize the chain rule whenever possible, and it's helpful to remember keep track of the independent variable. So, but it can also, I can understand why you just want to use y prime too. It's a little cumbersome. Especially here, I'd rather be working with y prime, with these fractions and all that. All right. Good luck on homework 2. I believe in all of you.